You know, I have always found it fascinating how the human mind works when it encounters a problem. We look at something enormous, something terrifying, and the very first thing we do is shrink it down to a size that feels manageable. We make it cozy. We make it solvable. We turn it into something you could fix on a Saturday afternoon with the right tools and a good attitude, and that is precisely what we have done with Mars. People talk about terraforming Mars the way you might talk about renovating an old house. Move in, knock down a few walls, patch the roof, maybe put in some new windows, plant a garden, wait a few centuries, breathe the air. It sounds reasonable when you say it fast enough. It sounds like an engineering problem, like something with a budget and a deadline and a project manager sending progress reports. And I am here to tell you, with the full weight of everything physics has taught us, that this picture is not just wrong. It is wrong in the most spectacular, most educational, most beautiful way a picture can possibly be wrong. Because Mars is not a fixer-upper waiting for motivated new tenants. Mars is a planetary crime scene, and the perpetrator is the fundamental architecture of the universe itself. Let me give you the first thing you need to truly sit with. When you stand on Earth and breathe, what you are doing is interacting with the product of a very specific, very improbable planetary configuration. You are breathing the result of a planet with the right mass, the right internal engine, the right chemical inventory, and the right position in a solar system that had the patience to cook all of these ingredients together over 4.5 billion years. You did not get lucky, you got physics. And the moment you truly understand what physics actually did to produce this air around you, you will never look at a picture of the Martian surface the same way again. I want you to think about a bicycle tire. A big one, the kind you would find on a heavy touring bicycle, built to be inflated to serious pressure. Now imagine that tire has been sitting in a workshop, and while it sat there, someone took an extremely fine needle and pushed it through the rubber in 1,000 different places. Not big dramatic holes you can see and plug. Tiny, microscopic punctures, the kind where the rubber looks almost normal but the structural integrity is completely, permanently compromised. Now imagine you need to inflate that tire. You pick up a small plastic hand pump, the kind you keep clipped to your frame for emergencies, and you start pumping. And while you are pumping, you are not standing in a quiet garage. You are standing in the middle of a violent, roaring hurricane, and the wind is not simply blowing around you, it is physically grabbing the air coming out of your pump and flinging it away in every direction before it can even settle inside the tire. You pump harder, your arms ache, you pour everything you have into that tiny pump. And the pressure inside the tire rises for a moment, and then falls, and then rises a tiny bit less, and then falls again. Because the rate at which air escapes through 1,000 tiny punctures in a hurricane is not slower than the rate you can push it in. It is faster. Reliably, inescapably, mathematically faster. The holes win. They will always win. Not because you are weak, but because the arithmetic of the situation does not care about your effort. That tire is Mars. The hurricane is the sun, and the pump is every terraforming scheme, every thermonuclear device, every comet redirecting mission, every dream of an engineered sky that any science fiction writer or aerospace visionary has ever sketched on a napkin. Now let me show you precisely why the tire leaks and why the punctures cannot be repaired. The first truth is one of the most gorgeous pieces of physics ever written down, and it goes by a name that sounds almost literary: genes escape. And it begins with something you already know, something you learned in school but perhaps never truly felt in your bones. Temperature is motion, not a metaphor, not an analogy. Literally, precisely, identically the same thing. When we say that a gas is at a certain temperature, what we physically mean, down to the level of individual molecules, is that the atoms and molecules in that gas are moving. They are vibrating and bouncing and colliding at a certain average speed. A hot gas is a fast gas. A cold gas is a slow gas. The temperature number on your thermometer is just a way of counting the average kinetic energy of an enormous collection of tiny, jiggling, careening particles. Now here is where it gets interesting. The word average is doing enormous work in that sentence. When you have a huge population of gas molecules moving at some average speed, you do not have a population where every single molecule moves at identically that speed. You have a distribution, a spread. Some molecules are moving slower than average. Some are moving faster, and some, just by the random statistical luck of collisions and near misses, are moving much, much faster than average. This is not a small effect. The distribution of molecular speeds in a gas, which carries the name of the Maxwell-Boltzmann distribution for the two physicists who worked it out, has a tail. A long, thin, energetic tail where a measurable fraction of the molecules at any given moment are moving significantly faster than the average. Now ask yourself this: what happens to a gas molecule that is moving upward, moving away from a planet, and moving fast enough that the planet's gravity cannot pull it back? It leaves. It simply leaves. It escapes into space and never returns. And this is not a dramatic event. There is no explosion. There is no announcement. An atom of oxygen or a molecule of carbon dioxide reaches the top of the atmosphere, happens to be pointed in the right direction, happens to be moving at that particular moment with enough velocity to exceed the escape velocity of the planet, and it is gone, forever. One fewer atom in the atmosphere, one tiny decrement in a ledger that has been running in the red for billions of years on Mars. Now let us talk about the math of escaping, because this is where planetary mass becomes the controlling factor in a way that cannot be negotiated or engineered around. The escape velocity of a planet, the minimum speed an object needs to be moving to break free of a planet's gravitational pull and never return, depends on two things: the mass of the planet and the radius of the planet. More mass means a deeper gravity well, means a higher escape velocity, means molecules need to be moving faster to get out. Less mass means a shallower well, means a lower escape velocity, means molecules can escape at lower speeds. Mars has roughly 1/10 the mass of Earth. 1/10. The escape velocity of Mars is about 5 kilometers per second. The escape velocity of Earth is about 11 kilometers per second. More than double. Now go back to that distribution of molecular speeds, that Maxwell-Boltzmann tail. On Earth, the fraction of oxygen molecules in the upper atmosphere that happen to be moving faster than 11 kilometers per second at any given moment is genuinely, almost unmeasurably small. The tail of the distribution does exist out there, but it is so thin, so sparse, that the rate of atmospheric loss through Jean's escape on Earth is negligible over any human timescale. Our heavy gravity protects us by demanding that molecules need an enormous amount of kinetic energy to escape, energy that the vast majority of them simply do not have. On Mars, you only need 5 kilometers per second. That is a very different place on the Maxwell-Boltzmann curve. The tail of the distribution is much fatter there. A much larger fraction of molecules at any given temperature exceed that threshold. And lightweight gases, hydrogen, helium, and atomic oxygen are especially vulnerable because lighter molecules at the same temperature move faster. A hydrogen atom at the temperature of the Martian upper atmosphere is frequently, routinely, statistically hitting escape velocity and vanishing into the void. And here is the thing that should settle this matter permanently in your mind. You cannot change the mass of Mars. You cannot add mass to a planet in any quantity that would meaningfully deepen its gravity well. The mass of a planet is not an engineering parameter, it is a geological and cosmological fact, frozen in place by 4.5 billion years of solar system history. The Martian gravity well is the Martian gravity well. It is shallow, lightweight gases fall out of it continuously. That is not a problem to be solved. It is a statement about the nature of reality. Even if you filled the Martian sky with oxygen and nitrogen today, right now, this instant, you would be watching a very slow-motion leak, not a catastrophic collapse. A persistent, quiet, relentless drain. The thin tail of the speed distribution, molecule by molecule, would begin bleeding your atmosphere back into deep space. Over hundreds of thousands of years, over millions of years, the atmosphere would diminish. And this is before we even discuss the second catastrophe. The second truth is the one that fills me with genuine awe, because it involves a physical phenomenon so enormous and so alien to everyday experience that most people simply do not have a category in their mind to put it in: the solar wind. You think of the sun as a thing that shines, a hot, bright ball that sits at the center of our solar system and sends us light and warmth, and it does do that, but it also does something else, something relentless and invisible and violent. It breathes, it exhales. It constantly, continuously, perpetually ejects a stream of charged particles, mostly protons and electrons, outward in every direction at speeds of several hundred kilometers per second. This is not sunlight. Sunlight is electromagnetic radiation, photons moving at the speed of light, carrying energy but no mass. The solar wind is matter. Actual particles with actual mass, moving at a significant fraction of a percent of the speed of light, plowing outward through the solar system in all directions, hitting everything in their path. The Earth is in the path of the solar wind. Right now, this very moment, the Earth is being hit by the solar wind constantly, and has been for as long as the Earth has existed. And yet our atmosphere has not been stripped away. And yet the air you are breathing has not been slowly eroded into space by a constant barrage of high-energy protons. Why? Because the Earth has a magnetic field. A powerful, planet-wide dipole magnetic field generated by the motion of liquid iron in the outer core, driven by the heat of the interior and the rotation of the planet. This magnetic field extends far above the atmosphere, wrapping the Earth in an invisible protective bubble called the magnetosphere, and when the solar wind hits the magnetosphere, the charged particles are deflected. They follow the magnetic field lines around the planet, pushed sideways, redirected, funneled toward the poles where they create auroras, but fundamentally prevented from striking the upper atmosphere directly. The magnetosphere is not decoration. It is not a bonus feature. It is the single most important piece of planetary infrastructure that stands between our atmosphere and complete destruction. Mars has no magnetosphere. Mars once had one. The early Mars, billions of years ago, was a geologically active planet with a molten, churning core that generated a global magnetic field. Early Mars was warmer and wetter and had a thicker atmosphere. The evidence for this is written in the ancient rocks of the Martian highlands, in the patterns of magnetic striping frozen into the crust from that ancient era, in the presence of ancient river channels and lake beds carved by liquid water, but then the core cooled. The interior of Mars, being a smaller planet with less internal heat than Earth, radiated its thermal energy into space, and slowly, over hundreds of millions of years, the convecting liquid iron in the core slowed and solidified. The electrical currents that generated the magnetic field weakened and stopped. The magnetosphere collapsed, and when it did, the solar wind had direct access to the Martian atmosphere. The process that followed, that has been following for the past 4 billion years, is called ion stripping or sputtering, and it works like this. When high-energy solar wind particles hit the upper atmosphere of Mars, they collide with atmospheric molecules. These collisions transfer energy. An oxygen molecule in the upper atmosphere that gets hit by a proton moving at several hundred kilometers per second receives a significant energy kick. It can receive enough energy to exceed the escape velocity of Mars, and it leaves. Moreover, the ultraviolet radiation from the Sun, which the magnetosphere also partially deflects, and which the ozone layer absorbs on Earth, hits the Martian upper atmosphere directly. Ultraviolet photons ionize gas molecules, stripping electrons from them and making them electrically charged. Charged particles are directly accelerated by the electric and magnetic fields associated with the solar wind, and they can be pulled off the planet entirely. The result is a continuous, powerful 4 billion year erosion of the Martian atmosphere by the solar wind. NASA has measured this directly. The MAVEN spacecraft, specifically sent to Mars to study atmospheric loss, measured the rate at which Mars is currently losing its atmosphere to the solar wind. It is not a theoretical concern. It is an observed, measured, ongoing process. Now I want you to think about what this means for terraforming. You pump gas onto Mars. You spend unimaginable energy melting ice, releasing carbon dioxide, importing nitrogen from Titan, whatever scheme you have. You build up a thicker atmosphere. And the solar wind hits that thicker atmosphere and strips it away. The rate of stripping is not fixed. It scales with the amount of atmosphere present, with the solar activity, with conditions that vary but never stop. You are not filling a container. You are pouring water into a pipe with one end open to a vacuum. Without a magnetosphere, any atmosphere on Mars is not a stable construction. It is a temporary condition, and you cannot restart the Martian dynamo. The core is cold, the iron is solid. There is no engineering intervention that puts the heat back in the interior of a planet. You cannot reheat a planetary core with any technology available or theoretically conceivable. The dynamo is dead. It has been dead for 4 billion years. The solar wind will keep blowing for another 5 billion years. The arithmetic of this situation is not complicated. The third truth is more subtle but no less absolute, and it addresses the material question. Even if you could somehow slow the atmospheric loss, even if you invented a giant artificial magnetic shield and positioned it at the Mars-Sun L1 point and actually managed to redirect a significant fraction of the solar wind away from Mars, you would still face the problem of where the atmosphere comes from in the first place. Building a thick, warm, breathable atmosphere requires raw materials. It requires volatile compounds, gases, water, carbon dioxide, nitrogen, oxygen, the chemical ingredients of a biosphere. And Mars is, by geological and geochemical accounting,